Hi, my name is Kunal Khallar, and this is my project, Handwritten Digit Recognition. The goal of this project is to recognize handwritten digits from 0 to 9 using deep learning. The input is a 28 by 28 grayscale image, similar to the MNIST dataset format, and the output is the predicted digit class. Now, this is a multi class image classification problem. I built this project as a complete machine learning pipeline, not just a single model file. It includes data loading, model architecture, training, evaluation, prediction, configuration, testing, etc. Uh, this README file describes it as an end-to-end pipeline for recognizing handwritten digits from 0 to 9 using MNIST style 28 by 28 images. I provided in the internship portal and you can read it from there. Now I'll quickly explain the project structure. The SRC folder contains the main project modules. The model.py, this file contains the neural network architectures like MLP, CNN, and deep CNN. The data loader.py, this file handles MNIST loading and data augmentation. Then comes the train.py. This file contains the training loop, including checkpointing, training utilities, etc. Then comes the evaluate.py. This file handles metrics like confusion metrics, classification report, and misclassified samples. Then comes the predict.py. This file is basically used for single image inference. Then comes the util.py. Uh, yeah, the utils.py. This file contains helper logic like seeding, device selection, average meter, early stopping, checkpointing, etc. And at last comes the config.yml. This file stores hyperparameters, so I can change the training settings without changing the main code. The README lists them. The README lists these same modules and describes main.py as the unified CLI entry point. Now let's look at the model.py. So this project supports basically three model architectures. The first one is MLP, which is the baseline model. It basically flattens the 28 by 28 image into 784 input features and passes it through fully connected layers. This is simple, but it loses some spatial information from the image. Uh, the second, the second one, the second model is the CNN, which is the recommended model actually. The CNNs are better for images because convolution layers can learn local patterns like edges, curves, and strokes, like that. And in the CNN architecture, actually, the image passes through basically two convolution blocks. So this is block one and this is block two. Each block uses convolution, batch normalization, ReLU activation, max pooling, and dropout. After that, the features are flattened and pass through the fully connected layers to produce 10 output logits, one for each digit. Third model is Deep CNN, which is a deeper version of more convolutional blocks and higher capacity. According to the README results, it gives the highest accuracy. So the README says the CNN has two convolution blocks followed by a fully connected head, while Deep CNN has three convolution blocks with increasing channel widths. Now I'll explain the training pipeline. The model is basically trained on the MNIST dataset. According to the README, the dataset is split into 90% training and 10% validation. The project saves checkpoints after epochs and keeps the best performing checkpoints as the file models slash cnn underscore best dot pth. The configuration file controls the important hyperparameters like model type, uh, number of epochs, batch size, learning rate, optimizer, scheduler, augmentation, AMP, and early stopping patience. For training, the project uses cross entropy loss with label smoothing. The Adam optimizer with way decay, one cycle LR scheduling, gradient clipping, and atomic mixed precision on CUDA. These techniques help improve convergence, stability, and generalization. For evaluation, the project generates a classification report, confusion metrics, misclassified samples, and training curves. This helps analyzing not only the final accuracy but also where the model makes the mistakes. The README says evaluation generates classification report.txt, confusion metrics.png, misclassified PNG, and training curves.png. It also mentions cross entropy with label smoothing, Adam with weight decay, one cycle LR, gradient clipping, and AMP. Okay, so now I'll show the real demonstration of the project. Earlier, I trained the CNN model on CPU, and after two epochs, the validation accuracy reached at least 98.4 something percent, and the best checkpoint was saved as the CNN best.pth. Now I'm using this saved checkpoint for prediction by running the demo command. Actually, I've already run it, and it have made the result demo.png. So it goes as follows. Uh, yeah, so this command generated this result demo.png. Here the model is tested on 16 MNIST digit samples. Each image shows the predicted label, and uh, the true label. For example, this is the predicted label, the 7, and the true label is 7, so it's green. Now, the title says green, that means correct, and red means wrong. In this demo output, all shown predictions are green, which means the model predicted these samples correctly. For example, 2 as 2, 1 as 1, you know, let me show you 9. So 9 as 9, 6 as 6. So coincidentally, it predicted all of them correctly. So this completes the full workflow of this project, loading the MNIST dataset, training a CNN model, saving the best checkpoint, and using that checkpoint to generate predictions. To conclude, this project is an end-to-end handwritten digit recognition pipeline using PyTorch. It supports multiple models like MLP, CNN, and Deep CNN, includes training, evaluation, prediction, configuration, and demo generation. I learned how CNNs are useful for image classification because they can capture local patterns like curves, strokes, edges, etc. I've also learned how to structure a machine learning project properly instead of keeping everything in one file. In the future, this project may be improved by adding a simple web interface where users can themselves draw a digit and get the live prediction.